First things first, looking at a laser can cause permanent eye damage. So be safe like me and get a weak laser and then also practice laser safety. I had heard that quantum computing was to be the next big thing. I didn't really understand it, so I wanted to know more about it, and I read a few materials. Unfortunately, linear algebra is my weakest area of math, and since everything tried to explain it in terms of linear algebra, my understanding did not get very far. What made things even more complicated was the fact that they talked about quantum computers that relied on spin, which actually has more to do with tiny magnets than actual spinning, and worse, is very expensive, so I couldn't just make my own quantum computer. Or so I thought. I was surprised and very pleased then to come across a video by Mithuna Yoganathan from Looking Glass Universe, in which she actually built her own quantum computer out of lasers. So then I used this plan and built my own quantum computer. She was able to do some things that a regular computer can't, but it was only 1 qubit and could not do entanglement, so that's still a ways away from a really good quantum computer. So here's a little briefing of how this works. Light is an electromagnetic wave, and it can wave in this direction, or in a perpendicular direction, or anything in between. The direction is called its polarization, and when I pass it through this polarizing filter, it forces the light to be in one of the perpendicular directions. The video from Looking Glass Universe goes into how polarizing filters works, but I'll skip over it for now. The in-between states can be mapped to the surface of the sphere, known as the Bloch sphere, with the north pole being the direction that can pass through, and the south pole being the direction that gets absorbed. We can turn the light in between these states, or we can kick back the phase in one of the perpendicular directions relative to the other. A material that can do this is called birefringent. 3 logic gates are all you need to do anything you want with a single qubit, and they are measurement, a gate that rotates the Bloch sphere around its x-axis by any angle you wish, and a gate that rotates the Bloch sphere around its z-axis by any amount you wish. That makes sense because every point has a latitude and a longitude, and if any angle you wish sounds like cheating, consider it as an infinitely small angle applied an infinite number of times, as many as you wish. Now the X gate is handled by literally turning the parts of the setup after the gate. However, you could also use a liquid crystal, just like the ones that are very likely in the screen that you are watching this on. As for the Z gate, you use the birefringent material for that. In the quantum computer from Looking Glass Universe, the birefringent material is thick enough to rotate the light exactly the amount that Mithuna Yoganathan wanted, but I have upgraded the quantum computer to rotate the light any angle you wish without varying the thickness. This creates a universal set of logic gates. Next, I will show you how I will prove that my Z gate works. I am starting by rotating the incoming light so it is halfway between the perpendicular states. Then, I will apply a certain amount of Z gate. And last, I will rotate the setup back an eighth of the turn the way it was. So if the Z gate was not applied, nothing happens. If the Z gate was applied at half a turn, the measurement is completely different. And if the gate is applied somewhat, then the measurement will be one way sometimes and the other way sometimes, resulting in a dimmer laser beam. So I have this birefringent wave plate with one of the axes labeled. And you will notice that as I tilt it back and forth in the laser one way, it dims to nothing and then brightens back again. And if I do it the perpendicular way, it'll brighten even more and then dim back to regular, indicating a full range of Z gate. You'll notice also that I got similar results with this piece of mica that my father literally found on the side of the road. The results for this is a little more noisy, but it's still a promising sign. I still need to figure out how to make entanglement affordable, but now that I'm a university student, maybe I'll find something interesting in the cool research I'm getting involved in that will help with that. Either way, I'm excited to see what innovative minds come up with in the advent of personal quantum computers.